Hello there, my name is Dion, and this video is about my final year project, Real-Time Brain-Computer Interface (BCI) for Robotic Systems. So, a bit more about BCI. BCI actually stands for Brain-Computer Interface. We interface our brain with the computer. The computer actually processes these signals and will be used for various applications. Our human body actually produces many signals throughout the day. One common signal is the EMG signals. These signals are produced by our muscles throughout the day due to our physical activities. Another type of signal is the EEG signals. Our brain activity produces these signals and can be captured through the scalp on our head. For example, as you are viewing this video, your eyes are taking in visual information and your brain are processing them. This produces many EEG signals on your head. With that, the objective of this project is to develop real-time BCI for robotic systems. One of the applications for this project is a software simulation of a maze exploration game. The user is given an avatar and will be trying to reach the goal point. Secondly, we have a robotic system. This is a two-wheel robot and we will be controlling it. It can perform left, right turns, and forward movements. So, why do we want BCI in our lives? It is quite cool to do things like how superheroes do in the movies. However, that's not the main motivation of it. Physical disability is what some people around the world has. They have suffered nerve damage and have lost permanently the ability to move around. So, we have people who can't move their legs or arms freely. And some characters in movies, such as the movie Me Before You, the main character has suffered nerve damage and he can't move any part of his body apart from his head. So this technology helps such people around the world. Let's take a step back to the past research done in BCI. One common study is motor imagery. Subjects were required to imagine various physical actions in their mind. EEG signals were captured around the motor cortex of the brain, and they were processed and classified into various corresponding levels. The accuracies obtained for motor are commonly found between 50% to 60%. This is not reasonable for deployment for medical users. A group of researchers in India have started facial expression recognition research. They started by capturing EEG signals around the temporal region of the brain. These signals were then processed and classified accordingly to their facial expression. The accuracies obtained from their research ranges between 50% to 61%. The accuracies were not reasonable, thus they have found many ways to improve it. They started adding in gyroscope and started capturing EMG signals from the cheek muscles. The accuracy increased by an average of 15% across all their test subjects. This actually shows that we can improve the BCI accuracies with additional components. The amalgamation of EEG and EMG actually branches BCI into another category. Hybrid brain-computer interface involves both EEG and additional signals such as EMG. For this project, we will be exploring mainly on the EMG component for HBCI. We will be using common signals found on our head. We will be using jaw muscles and our eye muscles. Here is an overview of the entire system for this project. First, we have the signal capturing device. OpenBCI Ganglion 4-channel board is chosen because of its flexibility. It is able to capture both EEG and EMG signals. It is also able to choose various different channels as we please. Here we have a computer system which is a Windows 7 laptop, and it will be running OpenBCI GUI, which is a software from OpenBCI. It will be used to interface both the board and the computer. Internally, you will be streaming data to MATLAB using a LED streaming layer provided by BCI Labs. And on MATLAB, we will be using it as a platform for our maze game simulator. And from MATLAB, we can transmit various classification labels to our robotic system. You'll be using XB transceivers using Bluetooth. So here are the hardware components for our BCI system. First, we have the OpenBCI Ganglion board here, along with the electrodes to capture the signals. it will be powered by 4 AA batteries, and in this case we will be using rechargeable. And here is a CSR 4.0 Bluetooth dongle to connect both the BCI board and the computer. And here is a battery charger, and this is the conductive base to stick the electrodes onto our head. So this is the robotic system used in this project. It is Arduino controlled, and there is a Pololu dual motor driver shield used to control these two wheels. It is powered overall using a 6-volt battery, and it can be charged with this battery charger. To interface to the computer, Bluetooth connection is needed, so we will be using XP Bluetooth transceivers with the Explorer boards to interface with each other. Now, let's move on to the demonstration of this project. So over here we have the BCI GUI application. Over here you can see the time series which is streaming the data in real time, and over here is a FFT plot. This is actually done in real time, and you can see the energy of various signals at various frequencies. And here is the impedance check for you to check the connections, and here is a networking window. So first I'm going to change this to the LSL, which is a LED streaming layer, and change the data type into time series. So on my BCI board I have 6 electrodes, 2 for references and 4 for our signal inputs. I'm going to start with the references, which will go to the earlobes, and the other 4 signals will be at the temple of your head and the 2 frontal lobes, which is above your eyes. So I connected the 6 electrodes onto my head, and over here you can see the signals being streamed in real time, and the LSL is already started. So I'm going to my application made on NetLab. So for these demo purposes, I have made a new data set called demo, and I'll be showing you the training sequences. So for the training, it will start from left, right, and then forward, and finally stop. So this is actually one cycle. The training will take in 6 cycles, and so you have to do it 6 times. So let me show you.
Relax. Left. Relax. Right. Relax. Forward. Relax. Stop.
Okay, so that is one cycle. So it will be done 6 times whenever you want to train it. So for this demo, I have used my previously trained data, which is self-test, and here is the training results. So every time you run this, you will randomly pick 70% of the training data as the training set, and 15% as the test set, and the remaining 15% as the validation set. So the performance will vary over various users. So over here you can see the performance at 0.01. This is actually the error between the ground truth level and the predicted levels. And here you can see the confusion matrices. You can actually see the accuracies and the number of errors the system has made. So this is actually a very rare case that everything is 100%. Yeah, so every time you will be randomly choosing, so there will be cases where they will not be training any labels at all. For that case, you have to retrain it. So now let's move on to the applications of this project. The first is the maze game. So over here you will see the maze, and this is the avatar, and this is the goal point. So we are going to control it to the goal point by using the various actions you have trained. So left and right corresponds to left and right eye closing accordingly, and you will actually cause the avatar to rotate on the spot to the direction you want. And by forward movement, you are going to clench your jaws forward, and for it to stop, you just have to do none of the things you have trained. So now let's begin. And so you have seen here is I reached the endpoint of my avatar. You can see that it's actually not responsive at times. There's actually classification errors done by the neural network. So the accuracy from the training may not be the accuracy you get from the live testing because of the dynamic environment done by live testing instead of the training. So now is the application for the robotic system, and here you can see that the robot is moving, and I'll be trying to make it go around the bottle and come back to me. And that is a robotic application. To obtain the performance of this system, an experiment was conducted across 5 subjects including myself. Every subject have to train their own training profile, and they have to go through live testing sequences, and their accuracies were recorded. In the live testing, every class label will be tested 10 times at random to simulate a dynamic environment. The training results for all 5 subjects are as follows. Every subject managed to achieve an accuracy of 84% to 100% overall. Note that the training accuracy will vary per every session of training. This is due to the random nature of training data chosen. The live analysis accuracy is as follows over here. The accuracy actually ranges between 57% to 82%. This may be due to the tiredness of every single subject over the course of experiment. So we can see the differences in the training accuracy and testing accuracy. The testing accuracy actually maintains at 75% to 80%, and whereas the training accuracy were high and consistent throughout all test subjects. The drop in testing accuracy is significant, but it is still at a reasonable accuracy level. The fall in accuracy may be due to fatigue over duration of the experiment. The use of common EMG signals actually allowed desirable performance compared to conventional BCI. Overall, the project has achieved its objective of creating a real-time BCI system for robotic systems. We have seen the demonstration on how it works with the software and the hardware, and also the accuracies obtained from experiments have been significantly better than the conventional BCI. Thank you for watching this video. Have a nice day.